This is a second recording for section 11.7. This is about conditional probability. Sometimes the probability of an event, that should be an event, must be computed using the knowledge that some other event has already happened, which we actually used in the last section. War is happening. This type of probability is called conditional probability. The probability of event B given that A has already happened is written like this. So this is read the probability of B given A has already happened, right? If you wrote it the other way, probability of A given B, that's actually different. That's a probability of A given B happened. Here it's probability of B given A happened, which is also thought about of the number of elements in A and B over the number of elements in A. A has already, probability of B given A has already happened, so the number of elements that you're interested in is the number of elements in A. So notice that the denominator is the total number of elements in A. With conditional probability, the overall total is not necessarily the denominator. It's the total in event A. So we will see that conditional probability is a bit different than standard probability. So a letter is randomly selected from the letters in the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So the denominator is not going to be 26. We're not looking, we know, given that the outcome is a letter that precedes H. So what we want to know is the number of vowels preceding H over the number of letters preceding H. Okay? We want to find the probability of selecting a vowel given that the outcome is a letter that precedes H. So we only want that total here. We already know that it precedes H. So if you count those up, A, B, C, D, E, F, G, that's 7. You don't count H. Preceding H means before H. So that's A through G, and that's 7 letters. So we know that it's 7 letters, and the probability of a vowel knowing it's a letter before H, well, if you think about the vowels before H, that's, right, I would A, B, C, D, E, F, G. There's 2 vowels out of the possible 7. So with conditional probability, the denominator is not going to be the overall total, right? You have to look at just a specific subset. Mammography screening on 100,000 U.S. women ages 40 and 50 found that 720, it looks like, had a positive mammogram had breast cancer. 80 that had a negative mammogram still had breast cancer. Even though for 6,944, even though they had no breast cancer, they had a positive. All right, and we expect this one to be large. No breast cancer, negative mammogram, 92,256. All right, so it was a total, the total number of positive and negatives should be 100,000, and the total of breast cancer and no breast cancer should also total 100,000. Assuming that these numbers are representative of all U.S. women ages 40 to 50, find the probability that a woman randomly selected in this range has a positive mammogram given that she does not have breast cancer. So given that she does not have breast cancer. So we know for our denominator, it's the number of women with no breast cancer. All right, the denominator is not going to be 100,000. We know it's given that that she does not have breast cancer. We already know that, so it's not out of 100. It's out of the total number that have no breast cancer. So we look at no breast cancer and we look at positive mammograms because it says has a positive mammogram given that she does not have breast cancer. So that's 6944 out of that, which is this is breast cancer positive, the number of positive and no breast cancer. Okay, so just be sure to change the denominator. This no breast cancer, that's 99,200. So 6944 divided by 99,200. 6944 divided by 99,200. That should give you 0.07 on the nose. So there's a 7% chance of having a positive mammogram but not really having breast cancer. Find the probability that someone does not have breast cancer given that she has a positive mammogram. So this given is the denominator, okay? Given a positive mammogram, so that a positive mammogram is this denominator. That's the given. The given is always the denominator. It's only out of the people that had a positive mammogram, which is 7664, does not have breast cancer. Still that, right? No breast cancer with a positive mammogram. So you can see that these two are actually different. Has a positive mammogram given that she doesn't have breast cancer, or does not have breast cancer given a positive mammogram. The given is always the denominator. 6944 divided by 7664 is approximately 0.91. So this may seem high, does not have breast cancer given that she has a positive mammogram. This falls positive, but most people don't have breast cancer, so we expect that to be higher, right? Even though someone has a positive result, we expect them to really not have breast cancer because it's unlikely. It's less likely. All right, we have one last example in this section. From the sample space of the numbers, the digits 2 through 9. So you can see that that's actually 1, 2, 3, 4, 5, 6, 7, 8. All right, the number in the sample space is 8. A single number is to be selected randomly. Given the events, A, a selected number is odd, and B, a selected number is a multiple of 3. Find the probability as a reduced fraction. So this first one's not a conditional probability. We want the probability of B, i.e. the probability is a multiple of 3. So we are going to use the total number as our denominator. It's not a conditional probability. So there's 8 in the braces. We want the probability of multiple of 3. Remember, multiples of 3 are 3, 6, 9, 12, right, etc. So there's actually 3 of the 8 that are multiples of 3. And that's a reduced fraction, so we're done with that one. That is not a conditional probability. Here we want the probability of odd and a multiple of 3. This is also not a conditional probability. How many of them are odd and multiples of 3? 3, 6, and 9, but only 2 of them are odd and multiples of 3. Only 3 and 9 are odd and multiples of 3, but then of course we would reduce that to be a quarter. Now the last two are conditional probabilities. This is read the probability of B given A. So this is the probability, a multiple of 3, given A, so given that it's odd. So we know that the given is our denominator. So the number of odd numbers is the denominator. We are given that it's odd, so we are only selecting out of the odd numbers. We're not going to use 8 as the bottom. There are 3, 5, 7, and 9. So there are 4 of the 8 which are odd. So we only have 4 odd numbers. We already know, we are already given that it's odd. And remember that the number in the second one is the denominator, the number of odd numbers, when we first introduced that, right? The number in A is the denominator, or the odd numbers. Now we want a multiple of 3 given that it's odd. So of our odd numbers are 3, 5, 7, and 9. We want to know how many of them are multiples of 3. We already only looking at the odd numbers. There are 2 of the 4 that are multiples of 3, which reduces to 1/2. Again, when we first introduced that, it was the number of P and A over the number of A. All right, that's the formula. I hope for these that you don't have to use a formula, because the given relationship is the denominator. The number of that are odd and multiples of 3 over the number of odd. For this one, all right, this is read the probability of odd given B, which is multiple of 3, given multiple of 3. So the number of multiples of 3 is the bottom. All right, and when we look at our chart, 3, 6, and 9, there's 3 multiples of 3. And we want the probability of the odd given that it's a multiple of 3. So there's actually 2 of the 3 that are multiples of 3. If you wanted to use the formula, it's probability of A and B, or the number of elements in A or B over the number of elements in B. So there are 2 that are odd and multiples of 3 over the number in B, which is the number of multiples of 3, so which is of course 3. So that is the end of the conditional probability.